Hi everyone. I hope you had a very good lunch, and I hope to entertain you for the dessert now. So we have black hole mergers on our view. A particular kind of theory I will consider, cubic gravity in particular, Einsteinian cubic gravity, which is not in the title. Let me just start with a very quick motivation. I don't have to say much because, well, the theme of the day has covered most of this. So we've seen that there's a huge, a very vast landscape of modified gravity theories, and this talk is about that. Among those modified gravity theories, I'm interested in higher derivative corrections to GR. So the goal is very simple, is to test these theories, either to find something really new and exciting, or at least to constrain the scary landscape of theories that we now possess. How will I do that? I will use a recent approach developed by these people, Emparan and Martinez, which employs an extreme mass ratio regime, but in a way that is probably not the usual way that you are used to. And in the end, we only need to do ray tracing calculations to find the full evolution of the event horizon of a merger process. So let me begin by acknowledging my collaborators in this project. Antonia Frasino, she will be the next speaker, talking about similar topic but a different project. And two students, João Dias here in Lisbon and Valentin Pacoya in Perugia. So I will talk about this second paper, which is still in progress. Hopefully in 1 month or so it will come out. And I will break up this talk into 3 big parts. Actually, the first one is the largest one, the longest one. I will try to explain to you why we can indeed just use ray tracing techniques to find the full evolution of the merging event horizon. In the second part, I will give you a few details about the theory under consideration, this Einsteinian cubic gravity, ECG for short, and about black holes in that theory. And finally, I'll just present very brief results that we have right now. So if you've taken the course in GR, this picture should look very familiar. It's just a space-time diagram of a Schwarzschild black hole. So time runs vertically here in this picture. There's a singularity inside the black hole, and what are being drawn with these lines are the light cones at any given point. So the light cones are defined by an outgoing null radial geodesic and an ingoing null radial geodesic. So if you are a time-like particle, you would travel within your light cone. And the fact is that if you are sufficiently far from the black hole, measured here in radial distance, you just see normal light cones that you would draw in Minkowski spacetime, so 45-degree lines. But these light cones get tilted at a special place, which we call the event horizon. And beyond that point, well, you are forced to fall into the black hole. So this is a very normal picture, and you can think about an infalling particle, or say a particle in free fall. That's what's being represented here by this dashed line. And then you can go about and solve such an infall, use extreme mass ratio methods, and that's what we will do. But typically, one fixes the size of the large black hole, which is being described by this whole diagram, and one takes the size of the small particle to go to 0. We treat it as a particle. I want to do the opposite. So I want to resolve scales of the small black hole, in this case. That's the kind of object that I will consider. So I want to keep the size of the small object fixed, but if I want to take the extreme mass ratio limit, then I have to send the size of the large black hole to infinity. So that means that the horizon of the big black hole will be represented by an infinite plane. And the small black hole, which is represented here, it's basically, it is the same space-time diagram, but now it describes a small black hole. So you still have the horizon. Now I'm giving it a 3D perspective to it. So the horizon is a vertical tube. And you see I drew some outgoing light rays also, just to make the connection with the previous picture. So the immediate question is, what happened to the large black hole? Where's the big event horizon? If it's so big, we should see it somewhere. But the answer is very simple. Well, it's a plane. It's planar. The horizon is a null-like surface. It's a null hypersurface. So you just need to draw a null hyperplane in this figure. And you can draw it anywhere in time because you can use time translation symmetry that you have in the problem. So the picture that you should expect to get is something like this. The plane that I drew here is what you need to approach at late times. So the plane is fibered by null geodesics. The tube here represents the event horizon of the small black hole. It's also fibered by null geodesics. But of course, the whole spacetime is being deformed by the presence of the small black hole. So how do you find the event horizon of the full system? You just connect these two surfaces, which are indeed connected by certain null geodesics. So the whole name of the game is to find null geodesics that at late time approach this null hyperplane, and that provides us boundary conditions, and then integrate the geodesic equations back in time. Some of the geodesics will wrap up around the small black hole. So that was just a cartoon. This is an actual calculation. And indeed, it reproduces what I just described. You see, all of these are null geodesics. At late times, they approach a plane, a planar surface. At early times, they approach a kind of a plane in the past, but also you get kind of a tubular surface, which represents the small black hole. So here, the vertical axis is the time, and the other two axes represent space. Of course, I'm suppressing one dimension in order to be able to show you a picture. So once you have this picture, if you just take constant time slices, you get frames of a movie that I can show you. So up here, we are setting our coordinate system centered on the small black hole. The small black hole initially was disconnected from the large black hole, which is down here. Eventually they merge. And at sufficiently late times, any trace of the small black hole disappears. It fell into the large black hole. So this is an exact description in the extreme mass ratio, in the strict extreme mass ratio regime. Well, this neat picture has been applied to a few cases, non-rotating black holes first, in the paper I mentioned before, rotating black holes, but neutral, merger between a large black hole and a simple model of a star, charged black holes, so Rice and Norton black holes, and also for the case of a merger of a wormhole and a large black hole, which Antonio Frasino will tell you about in a few minutes, the next talk. So that's the kind of calculations that I will show you, but now applied to a very particular theory. It's a theory that I fancy. Let me tell you about the theory. So it's a higher derivative theory, which is naturally motivated at least as an effective low energy description of gravity when you don't know about the details of the ultraviolet completion. And in those theories, it's natural to organize the corrections to the Einstein-Hilbert term in terms of the powers of derivatives that you have. So you would have at first order in this expansion the terms that are quadratic in the Riemann, then terms that are cubic, etc. Now, I will not consider these terms, and there's reasons for that, but I will skip the reasons. You can ask me later if you want. I will consider a particular theory that includes only corrections that are cubic in the Riemann tensor. And it's a very particular combination of corrections. It has to be this combination with these very specific coefficients. Now, the interesting aspect about this theory is that it matches Einstein's predictions for linearized gravitational waves. So the spectrum of this theory around Minkowski is exactly the same as Einstein gravity. So that's why I'm interested in this theory. So what kind of black holes do we have in this theory? Actually, they're quite simple. There exist black holes that have the usual Schwarzschild form, which you should recognize here. They are described by a single metric function, which I call the blackening factor, F. But this blackening factor has to satisfy a certain equation that is obviously more complicated than the Schwarzschild solution. It has to satisfy this nonlinear differential equation that's written down here. Now the theory, I forgot to mention, and I'm sorry, I'll go back, has a coupling constant, which is dimensionless if you write it like this, lambda. So what I want to do is to make some predictions for the merger in this theory and be able to set perhaps constraints on the coupling lambda. So notice that if you set lambda to 0, all this term here vanishes and the only solution that you get is exactly Schwarzschild. So this theory for lambda equals 0 reproduces Einstein gravity with its own black hole solutions, as expected. Going beyond lambda equals 0, well, you have to solve that differential equation. It's not possible to solve it analytically, unfortunately, so you have to solve it numerically or resort to some approximation scheme, analytically in that case. In any case, what you find for the blackening factor is this kind of behavior, this kind of profile. So the red curve here is just the usual Schwarzschild profile, and the blue curves are the solutions that you get for various choices of the coupling constant. And you notice that as you increase the coupling constant, lambda, the 0 of this function, which identifies for you the location of the event horizon, grows. So black holes in this theory with fixed mass, if you tune up the coupling parameter, makes your black hole grow, actually. So you can expect that the mergers will feel this effect somehow. Okay, thank you. So all we have to do is repeat the same procedure that other people and ourselves did for other situations. So you have a fixed background. I will take the background I just showed you, and then study null geodesics in that background, obeying certain boundary conditions. Once we obtain the 3D picture, which it looks extremely similar to the one I showed you before, but it's not the same, you can take time slices to get, again, the 3D movie if you want. And you can study, that's what I will show you, the only thing I will show you, the time it takes for the merger to take place. So these are our preliminary results. I'm sorry, they're still preliminary, but it gives you an idea of what happens. So what I'm showing here in the vertical plot, in the vertical axis, is the duration of the merger, so how long it takes for the small black hole to fall into the big black hole, essentially, versus the coupling constant. And what you notice is that for small enough coupling constants, the merger is shorter than GR. So lambda equals 0 is the GR situation. So for this range of lambdas, the merger happens faster than in GR. But eventually for big enough lambda, order 0.25, something like that, the mergers take longer than in GR. So the hope is that we can use this kind of results. We have not done that yet, but we can use the time of the merger to set constraints on lambda, since the time of mergers is something that you naturally observe in gravitational wave detections. So I will end there. Maybe mention that that's one of the things we want to do. Another useful thing you can extract from these kind of calculations is just to serve as benchmark for actual numerical simulations, which we are lacking in, well, we only have in a very restricted class of theories right now. So this can serve as a benchmark for that. Thank you.
Any questions? Anybody? Hi, George. Thank you. I was wondering if anybody has looked, even going back to the GR case, at calculating the corrections that from your calculations that you would get from coming away from the extreme mass ratio.
So no, the short answer and true answer is no. Nobody has done that, and it's something that is obviously lacking. Because in this extreme mass ratio, what happens is that we're just calculating null geodesics in a fixed background that is static.
Right.
There's really nothing happening. There's, in particular, no gravitational waves. And so by going to this strict limit, we are losing all signs of gravitational waves. So that's part of the long-term project, is to go beyond the strict extreme mass ratio limit to actually be able to say something about gravitational waves.
There isn't a sort of principal obstruction to that that's known or seen. It should be doable.
There's no principal obstruction. Yeah, it's just harder.
Well, good luck.
Well.
Thanks. I had a quick question and maybe a longer question. So the quick one is, I think no one has done these theories in numerical relativity, presumably because they don't necessarily have a well-posed formulation because it's higher derivative.
Yes,
okay.
Yes, I agree.
Okay.
Or at least we don't know how to. Right?
Sure, not yet. And then my other question was do you have a feeling for why it goes up again, like in terms of the length of the merger? Because I think it made sense to me it goes down because it somehow gets bigger, but then I didn't really understand why it would go up again for the time of the merger.
I'm not sure if I can give you a full answer, but I have some ideas about that. So there are several competing effects here. And you can see that already here. For example, it's true that the size of the object grows as you increase the coupling constant, but also the gravitational potential is softened. Yeah. So there's a competition of effects. Another thing I can say is that other people have studied, for example, the deviations of these black hole solutions from just GR solutions, and there seems to be a maximum coupling, lambda, so a lambda that gives you the maximal deviations. So in that sense, it's natural that you get non-monotonic behavior.
Okay, thank you.
Thank you.